Okay, today we are going to start 7.4, which is applications of logarithms and exponentials. Pretty much just story problems or how you would actually use them. And actually, it's really good timing because if you have been watching the news lately with all of the coronavirus going on, you probably would have heard about how it is an exponential function. So it started off slow and then people kept getting sicker and sicker and sicker at a faster rate. So we are going to kind of see how those models work that they've been using in the news. But so we're going to start off with exponentials first, and then we'll look at some logarithm problems. But two types of exponential problems that you will see is you have exponential growth, which is what I was just talking about with like the coronavirus, where you're starting off slow and then it speeds up until it's spiking really fast. Then we also have exponential decay, which is where it starts off really steep and then it starts to slow out. You'll see these a lot in like chemistry problems. They use a lot of exponential decay. So for exponential growth and exponential decay, they are all going to be using exponential equations, which are in this format: y equals a times the base to a power of x, where this a, if it's greater than 0, and if b is greater than 1, then it's going to represent exponential growth. So that's kind of how you can tell if it's growing. If a is greater than 0, but b, the base, is between 0 and 1, so either a fraction or a decimal, that's when you're going to get exponential decay. So that b is going to be telling you whether it's growing or decaying. So again, if it's bigger than 1, it's exponential growth. If it's between 0 and 1, then it's going to be exponential decay. So let's scoot this down a little bit. Okay. So when you have exponential growth, the base, b, that we were just talking about, that's what we call the growth factor. So again, if that growth factor is bigger than 1, then it's going to be growing. If it's between 0 and 1, you're going to have that exponential decay. And in that case, we call it the decay factor. We're very original with our terming in math. And another way we use exponential models is actually with money and interest. So you might have seen something like this before if you've taken like a business class. But we're going to look at some problems using this model right here. So if you have a of t, which represents the amount of money after time, that equals little a, which is your initial amount of money that you'd be like investing or something, times 1 plus r. And r here is the rate. So think of like the interest rate, how fast it's growing, or if it's decaying, which would be bad in the case of money. And then to the power of t, where t is time. So again, a, capital A, stands for your amount after a certain amount of time. Little a represents your initial amount. R stands for your rate, so think of like the interest rate, and T represents for time. So for growth or decay to be exponential, a quantity changes by a fixed percentage each time period, and that's that rate that we're talking about. So we're going to be using equations like that today. So let's look at some problems using exponential growth. Okay. So it says you invested $1,000 in a savings account at the end of 6th grade, which how cool would it be to be a 12-year-old and have $1,000? The account pays 5% annual interest. How much money will be in the account after 6 years? So for this one, we're going to use this formula. A of t equals little a times 1 plus r to the power of t. And then we'll just kind of give all of the different numbers the appropriate variable. So we initially deposited $1,000. That's going to be A. And then R, again, that's your rate, is 5%. But remember, when we work with percentages, we want to move that to a decimal form. So 0.05. And then they told us the time we're looking at. They want to know how much will be in there after 6 years. So if we plug all of that in, the amount after 6 years will be 1,000 times 1 plus 0.05 for the rate to the power of 6. And then we're literally just going to plug this into the calculator. It's kind of just a plug and chug problem. So 1,000 times 1 plus 0.05, all to the power of 6. And we have this much money. So it just depends on what they ask you to round to. Sometimes it's like the nearest dollar. So we'll just say it's about $1,340. I guess you could say like 10 cents if you wanted to round up. So we would have, after 6 years, $1,340 and almost 10 cents. And that is it. So really not too bad, these story problems. Okay, let's try another one. Suppose that a new employee starts working at $6.99 an hour and receives a 4% raise each year. After time t in years, his hourly wage is given by this equation, $6.99 times 1.04 to the power of t. You'll notice this is the equation we were just working with, where here's your initial amount, and then the interest rate, or the rate we're using, 4%, is 1 plus 0.04, which is 1.04 to the power of t. So they're saying find the amount of time after which he will be earning $10 per hour. So how much time will it take to get to that hourly wage if he started at $6.99? So if we're using that same format as the problem above, we know what we want the answer to be. We want this to equal $10. So we're saying, when will it equal 10? So we're starting with the $6.99 times 1.04 for that 4% to the power of t. So this one we're actually trying to find, what is t here? What are we looking for time? So we're just going to start solving backwards. We want to get t alone. So first we want to get rid of this $6.99, and it's being multiplied, so we'll divide it on both sides. So 10 divided by $6.99 is, we'll just do 2 decimals, 1.43, and then those cancel, and we get 1.04 to the power of t. Okay, and then when we've been practicing solving our equations in the last section, I told you guys that whenever your variable is up in the exponent like this, we need to get it out of the exponent, and the only way to get it out of exponential form is to go to log form. So that's going to be kind of one of the tricks this unit that you want to work on learning. So I want to get this to where I can actually start solving for it, and the only way to do that is by going to log form. So right now the 1.04 is our base. That's going to be the base of the logarithm. So I'd have log of 1.04 as your little subscript. And then this goes on the inside, and then your exponent becomes your answer, which is kind of nice because that's what we're trying to isolate. So now to figure out what t is, we just literally have to throw this into our calculator. So you can either do the base change on your calculator, or you can go into math and get that log base. And our base is 1.04, and then what was it, 1.43 on the inside. And so we get 9.1, which is a long time. So 9.1 years. If that was me and it was going to take me 9 years to get to $10 an hour, I'd probably be looking for a different job. Okay, let's do one more of these exponential ones before moving on. Hey, if you have taken some science classes, you might have seen problems like this already. It's talking about the amount of carbon-14, and how much of it is decaying in a bone, so you can figure out how old the bone is. So you might have done stuff like this in your science class. But it says the amount of carbon-14 in an object is given by this equation. Y equals A times E to the negative 0.00012 t, where A is the initial amount of carbon-14, and then T is the age of the bone. So they told us a fossil bone that they found has 29% of its original carbon-14. So what is the approximate age of the bone? Hey, the setup on this one can be a little bit tricky because they gave us this equation to work with. A times E to the negative 0.00012 t. And then they've told us that the bone contains 29% of the original carbon-14, but we don't know what the original carbon-14 was because we weren't there to have the initial bone. So we have to use this little 29% to kind of think backwards a little bit. What we're looking for is, well, we know what the bone already is. That's what Y is. We know our bone contains 29%, or 0.29, of whatever its original amount of carbon-14 is, which is A. We don't know what A is, but that's okay. We don't actually need to know it, because we know that the bone now has 29% times whatever it had originally. But since Y is equal to that, we can substitute this 29A in for Y right here. So we're going to put 0.29A, what the bone's already equal to right now, times A e to the negative 0.00012t. This is how much carbon-14 we have now. This is how much it originally had. But since I have an A on each side, if I start dividing by A, they end up just both canceling out, which is why we don't really need to know the original amount of carbon-14, because it kind of just goes away anyways. So we have 0.29 is equal to E to the negative 0.00012t. And then we're still trying to solve for t, which is in the exponent. So just like the last problem, whenever your variable is in the exponent, the way to get it out is to go to log form. Right now we have a base e. The log form for base e is the natural log. So the natural log, and we don't have a little subscript on this, it would be an e, but we don't write it. This is going to go on the inside, the 0.29, and then the exponent comes down to what it's equal to. So then on this one, still solving for t, I need to get rid of this decimal by dividing by a negative 0.00012 on both sides. So that those cancel. And then we're just going to throw this part into our calculator. So the natural log button is just next to the number 4 in your calculator. You get the natural log of 0.29 divided by a negative 0.00012. And that is the age of our bone, so about 10,300 years old. So 10,315.6 years. And that's how they do carbon dating for fossils. So, hey, we'll move on now. Hey, let's look at some log problems now. It's actually kind of funny. When all this went down, we were talking about the coronavirus on the news, and then we happened to have earthquakes on top of it, which are a log scale. You guys probably didn't know that. But when all this was going on, I was like, hey, at least this will be really cool for our logarithms. You know, we're going to have all of these applications that we can actually look at. So the Richter scale that they measure earthquakes in, the magnitudes of earthquakes, the difference between the earthquake strengths is actually really, really big. So to make that scale a little bit easier to understand, they use logarithms to kind of downsize the numbers so that it's easier to report the size of the magnitude. So on the Richter scale, you'll hear like, oh, the earthquake had a magnitude of, like, I think, what was it, 4.3 that we just had. And so that would be on the Richter scale, but then down here is what the actual energy being released is. So it's a lot bigger of an energy than the Richter scale kind of leads you to believe. So when we're going through these earthquake scenarios, you can actually figure out the difference in strength, or how much energy is actually being released in the earthquake, by doing logarithms. So remember, though, a common logarithm is with a base 10. We just don't write the base because we're lazy. So instead of doing log base 10, we just do log of x. And then because many measurements of physical phenomena have such a wide range of values that the reported measurements are logarithms of the values, not the actual values. Again, it kind of makes it a smaller scale, which is easier to work with. So the Richter scale is one of those. So let's look at a problem. So it says, in December 2004, an earthquake with magnitude 9.3 on the Richter scale hit off the northwest coast of Sumatra. So here's a little picture of it. The diagram shows the magnitude of an earthquake that hit Sumatra in March 2005, a year later. So this formula right here is the formula you will use in any earthquake problems that you're going to come across in your homework. So it's I1, which stands for intensity 1, over I2, intensity 2, is equal to magnitude 1 minus magnitude 2. So these are the intensity levels that are picked up by the seismograph, and then these are the magnitudes on the Richter scale. So they're saying how many times more intense was the December 2004 earthquake versus the March 2005 earthquake. So those numbers they gave us, this 9.3 is going to be our magnitude 1. And then the magnitude 2, they didn't say in the story problem, it's actually in the picture over here. It's 8.7, so I'll just write that out. It's kind of hard to see in the picture. So we're going to take these two numbers, the 9.3 and the 8.7, and just plug it in here. Hoping I forgot to write the log next to this. We have log of I1 over I2. We don't know what those are. Those are the intensities we're trying to figure out. Is equal to the two magnitudes. So we have the 9.3 minus the 8.7. And then we're solving for the intensities right here. This is pretty easy. We just subtract the two. 9.3 minus 8.7, which is 0.6, is equal to our logs of our I1 over I2. Okay, and then here, whenever your variables are inside the logarithms, the way to get it out of the logarithms is to go to exponent form. Sorry, I have my window open. I don't know if you guys can hear that loud truck that just drove by. When the bases are in, remember it's a base 10. So if I'm going to exponent form, that 10 becomes the base in my exponent. This is what becomes the exponent, the 0.6. And then the part on the logarithm is what it's going to equal, I1 over I2. So if I put this in my calculator, 10 to the power of 0.6, we get 3.98. So what this is saying is that the two intensities, since they're being divided, I could think of isolating the I1 by timesing by I2 on each side. And you're saying that intensity 1, the first earthquake, was 3.9 times as strong as the second earthquake. So, oh, can you guys even see what I'm writing? Sorry. Scoot that up a little bit. It's hard when I'm not with you guys and you can't just yell at me to move. Okay. So, the first earthquake was 3.98 times stronger than the second earthquake. So really, even though on the Richter scale, there was only a 0.6 difference between them, the intensity was way stronger. So it was 3.98 times as intense. And I wanted to do this with the actual earthquakes we just had in Utah, if we had extra time. Or maybe I should have just changed the numbers and we could have figured out how much more intense those earthquakes were when we had the original big one versus the ones that followed. But that Richter scale can sometimes be misleading again because it doesn't seem like it would be that big of a difference when it's only 0.6 away on the Richter scale. But actually to have the ground shake that many, practically 4 times more intense would be quite a big difference. So kind of interesting there. Okay, another type of logarithm we're going to look at is the pH scale. So again, if you have been doing like chemistry or something, you probably have seen this formula before. So the pH formula that you might have seen in your classes is actually a log as well. So this equation is what you're going to be using. It's a pretty easy one. Negative log of your hydrogen ions. So, and they will give you that number. So the pH substance equals that negative log of the hydrogen ions. And on this problem, it says for household ammonia, you have 10 to the negative 11 power of hydrogen ions. And then for vinegar, you have 6.3 times 10 to the negative 3. So what's the difference of pH levels for ammonia versus vinegar? So first we need to figure out what the pH levels are for each one. So let's do the ammonia first. So we are literally just going to take this number they gave us for the pH and the hydrogen and plug that in. So we're going to have negative log of 10 to the negative, oh no, I wrote over it. I think it's negative 11. And then we'll just throw that into your calculator and that's going to equal our pH. So don't forget your negative, but negative log of 10 to the power of negative 11. And we get 11 for the pH. And then for vinegar, we're going to do the same thing. The hydrogen for this one was this number right here, 6.3 times 10 to the negative 3. So we just plug that into that formula. The nice thing about this is it is a base 10, so you don't have to do any weird base formulas for it. Negative log of 6.3 times 10 to the power of negative 3. And we get about 2.2. And they just said, what is the difference of the pH level? So you're literally just going to subtract the two. So 11 minus 2.2 is 8.8 difference. So when you see those pH problems, they are very straightforward. They're not difficult at all. Okay. And then the last type of log problems that we're going to look at is with sound, with decibels. They are also based on a log scale. So the loudness in decibels of a sound is defined as this formula right here. Let me write it a little bit bigger. 10 times log of I over I naught, just a little zero subscript, where I in the numerator is the intensity of sound in watts per meter squared, and I naught is the intensity of a barely audible sound. So that is given right here. So that's kind of like our constant that we're using. So I naught is equal to 10 to the negative 12. So you just kind of memorize that number. It's not going to change ever. So now for the problem, it says town regulations require the loudness of construction work not to exceed 100 decibels. Suppose a construction team is blasting rock for a roadway. One explosion has an intensity of 1.65 times 10 to the negative 2 watts per meter squared. Is this explosion in violation of the town regulations? So let's check and see. We need to see, is it over 100 decibels? So that's going to be the intensity of the explosion that goes in the numerator. So we have 10 log, and then I'm going to plug that number in, 1.65 times 10 to the negative 2. And then the I naught, again, is just going to be this kind of constant, 10 to the negative 12, that you'll just memorize. So we just are going to, again, plug and chug this in and see if it fits within the regulations. So 10 times log of 1.65 times 10 to the power of negative 2. And that whole thing divided by 10 to the power of negative 12. And we get 102, which means it's just barely above the regulation. So since that was greater than 100, then yes, it violates the regulations. So those ones aren't too bad either. Just kind of plug and chug with them. Sometimes on the problems they will ask like these little things like, which physical value do you need to know to calculate, to answer the question? We needed to know what the intensity was of the blast, and then what value should you use for I and I naught? Well, I was the intensity of the blast. I naught is that 10 to the negative 12. That doesn't change. So pretty straightforward questions on those as well. Okay, and then that's actually it for today. So hopefully those story problems made sense. Hopefully they were a little bit interesting to you. Again, logarithms and exponentials get used all the time in lots of different ways, and I literally see them on the news all the time. We just had a pandemic breakout with exponential stuff, and then we have our earthquakes with the log stuff. So lots of different ways you can use these equations in real life. So hope you guys are safe and healthy. I'll see you later.